Okay, maybe we should start. Okay. Thank you everyone for coming to this STEM event. Again, before I'm going to introduce Dr. Carter, and then I would like to acknowledge gratefully, and then have all you guys coming, and then our library IT, John here to do all the video recording, and my support from our department, our library dean, and all my colleagues, my supervisor, and our AD that type here. And thanks again. And okay, Dr. Supporter Porter is an associate professor.
No, assistant.
Oh, and assistant. Okay, very soon.
Yeah, not there yet. Yeah.
Sorry about that. Assistant professor of the Department of Computer Science at Stony Brook University. He works in quantum algorithm, complexity theory, and cryptography. Dr. Porter earned his PhD in computer science from the Center for Quantum Technologies, National University of Singapore. He holds master in computer science from, I can't really pronounce the French, so I just ENSE Cachenry.
Yeah.
In France. Cachen, okay.
Yeah.
And Chanel Mathematical Institute, I believe in India.
In India,
right?
that's right, yes.
Prior to joining Stony Brook, Dr. Porter was a postdoc at University of Ottawa and at UC Austin. Okay, thank you for.
Okay, yeah, so I'll start. Welcome everyone. Yeah, thanks for coming. So this is going to be anyway like brief introduction to quantum. So I tried to make it like as general as possible, and I'll tell you like what I and my team are working. Okay, so basically we are seeing this buzzword right everywhere. Like I mean, the quantum computing, you know, like quantum advantage. What are these? So let's try to understand what are these. Okay. So essentially it starts with any object which is quantum, right? So when we think of like any object like which is quantum, maybe you can think of like electron, which is quantum, right? But the phenomenon that we want to use, the property that we want to use, it not necessarily has to be a quantum. Like it could be, you know, like maybe a semiconductor, you know, or, you know, like, or it could be like a photon. It could be, you know, like a some kind of pulse. Okay. So basically we are trying to capture some property. We don't really care about how it is implemented. Okay. At least from the theory perspective. So, so let's say like why we want to talk about this, right? Because we have like supercomputers these days, and supercomputers are really powerful. So why bother doing this new type of computing, right? So it came from this thing that the chart that here you are seeing is that this is actually a famous chart. It depicts Moore's law. Okay, it says that the amount of in nutshell, it says that the amount of computing power doubles every couple of years. Okay, so the kind of computer that we have right now, the computing power is going to double in just a few years. Okay, so just to give you one example, if you look at your phone that you are holding in your pocket, that is actually, believe it or not, that's actually faster than the supercomputers of 2010 even. Okay, so they were paying like billions to, you know, like have not billions, millions to buy supercomputers, and your phone is actually faster than that. Okay, so but then it has a problem. So right now you can go either way, right? You can either build larger computer, or you can put like more transistor into the semiconductor, and it's going to hit a limit, right? Because how many transistor you are going to put. And today the transistors are so small, the chips are so small, and it has so many transistors that, you know, it's kind of hitting the atomic level. And we are already starting to see quantum effect. So what microprocessor designers do, they usually try to, you know, try to mitigate those effects. They say like, okay, no, that is kind of, they look at as error, and they say like, you know, that's kind of affecting our computation. So let's try to do something to, you know, not use it. But the question is, what if you try to use that, right? What if you try to use the quantum effect that you are getting just by going so small scale? And that was actually the idea of famous physicist Richard Feynman. And so he was one of the many people who kind of envisioned quantum computer. Okay, so there were like three main points there. So one of the point was, if you want to simulate a quantum system, let's say you want to do some chemistry experiment, okay, or you want to you want to see if you want to, I don't know, you have some drug or something, okay, and then you want to see what's the effect of the drug. You have some small chemical reaction, you want to see how the chemicals are going to combine, okay. So all these things, if you want to simulate, what people do is that they use supercomputer. But supercomputer, being a classical computer based on Newtonian mechanics, it actually very quickly run into exponentiation. So the problem with these computers is that you cannot, simulate larger system. All you can do is that very tiny, small calculations. Okay, so the idea would be, if we build a computer based on quantum mechanics, then that would be ideal for simulating quantum physics, right? And in particular, like doing quantum chemistry experiments. So that would be one of the big selling point for quantum computer, right? It's like a direct application. Okay. The other thing is about the Moore's law that I was telling you, which is like the computation is actually, it's doubling every couple of years. So it's going to hit a limit. So then the question would be, what's next? Like, how would you, what we are going to do next? So quantum computer could be one of the solution there. All right. And the third point is like, if you go down really subatomic level, it becomes like, you are getting this power of quantum computer, power of quantum mechanics, so why not use it? All right. So based on these three ideas, he was thinking about coming up with a machine, okay, that could potentially be built one day. Okay. So so let's see like where we stand right now. Okay. So that was the idea that was proposed like around like 1980s. So this is the news article actually that I copied from like from the internet, and you see this is the article from like a couple of months back. Okay, so IBM is actually claiming that they have a machine with actually around 453 qubits. Okay, and what are qubits? So think of it this way: like if you use a normal machine, okay, it's based on small registers, right? Each register contains either 0 or 1. So qubit is like a register that contains quantum state, okay, just a single quantum state. So what IBM can do right now, they can build a quantum computer which is based on this 400 qubits. Okay, so the question is, what are we going to do with this kind of computer? All right, so let us see like what else we can do quantum computation for. So if you search the news, you will see that people are also trying to do ground to satellite based quantum teleportation. So quantum not only gives you the hope is not only to build a quantum computer, but also to try to take advantage of this quantum communication to do something that normally we cannot do with normal network. Okay, so the question is like, I mean, what kind of things we can do? So people are trying to build this thing. So let us see. Okay, so I'm going to tell you this. But then there are some downsides as well, okay, of having a quantum computer. So there is this news article which is saying that what hackers are doing is they are taking all the encrypted data that they can find and storing it in hard drive in the hope that when we have a full-fledged quantum computer, they are actually going to break and see what's inside. Okay, and this is actually coming from one of the famous phenomenon, one of the famous thing that happened in quantum computing, which is Peter Shor in 1994. He discovered an algorithm for factoring two numbers. Now you might ask, why do we care about factoring two numbers? That it turns out that the modern internet, so let's say you are doing some shopping in Amazon, right? You're sending your credit card information. The way it works is that you use some encryption scheme, and most of the time the encryption scheme is based on some variant of RSA. Okay, so RSA is like one algorithm, and it turns out that you can break RSA if you can factor large number. And quantum computer is actually, so Peter Shor actually found an algorithm which if you implement in a actually full-fledged quantum computer, then you can factor two numbers. In other words, you can break this kind of encryption scheme that we are using today. Now, why are hackers storing all the data? Is because even though all this data we cannot decrypt today, you can actually store it and keep it with you. And maybe in 2050, when we have, full-fledged quantum computer, you can run Shor's and break this data and see what's inside. Okay, so now people are trying to, move on and then move on from like RSA and then trying to come up with new crypto system that are like quantum resilient. Okay, but these are the things that is happening. So this is like one of the Wikipedia article that you can actually go and then see like what are the this list is not complete, but this gives you really nice timeline of what is happening in quantum computation. Okay, but see, like this is the news article from just 2 years ago, 3 years ago actually. So at that time, IBM and Google, they were claiming to build like 54 qubits quantum computer, 72 qubits quantum computer, and to break RSA, you need like, let's say, around like 2,000 to 3,000 qubit quantum computer. Okay, and you see that last year's article is that now they can do 400 qubits quantum computer. Okay, so the point is that we are kind of reaching there to have a full-fledged quantum computer. So of course, one application is U-factor numbers, but then the question is what else? What else are these computers going to be used for? Okay, so let us see, like, I mean, to understand like what these computers are going to be used for, we first need to understand what is really going on. What are these computers, right? What is quantum, like when we say? So so this is a nice analogy actually. You can think of normal computer as being this kind of switch. Okay, why do I say switch? It's because a switch, if you turn it off, the lights goes off, right? You turn it on, the lights goes on. And if you look inside normal computer like supercomputer or your phone or the laptop or tablet, like whatever you're using, all the data inside it are actually flown in this binary format. It's either 0 or 1. But in quantum mechanics, you can actually implement this kind of vector. So the data doesn't have to be only 0 and 1. It could be somewhere in between. So you could think of it as a vector in actually a complex Euclidean space. Okay, so it's like, think of it as a vector which can rotate in any direction. So that's the difference. In a sense, like it gives you more degree of freedom. You can think of quantum that way. But then you might ask, okay, what's the use, right? Like, okay, maybe 1 qubit is like, instead of being on and off, it could be this vector. What can we really do with it? So I'm not going to get too technical, okay, but I'll just show you like 1 or 2 slides of like what is really going on. So if you look at like 1 qubit system, that vector over there, okay, you can actually mathematically describe it this way. You can say that it has so 1 qubit system. Okay, I don't think. Okay, it doesn't work there. Okay, so 1 qubit system, you can actually see it this way. It's right. Do you see my mouse pointer? You don't, right? Okay. Maybe I'll try to go here. Okay, so you can think of it as that it is in the state 0, okay, with amplitude alpha 0, and it is in state 1 with amplitude alpha 1. Okay, what are these amplitudes? Think of it as like a probability. Okay, the only thing is that these probabilities could be a complex number. Okay, so this has this constraint that alpha 0 square plus alpha 1 square, they need to add up to 1. So if you go back to this picture over here, this vector, right, it is, see, it is in the middle, right? So it is 0 with certain probability, it is 1 with certain probability. So if the vector were to be over there, like this, then this is 0 with probability 1. If the vector is here, it is 1 with probability 1. But if it is somewhere in between, it could be 0 with certain probability, 1 with certain probability. Now the only thing is that it's a complex number, it's not a real number. Okay, so that's why we are doing alpha 0 square plus alpha 1 square. We want that to be 1. If it were like normal probability, we would have want alpha 0 plus alpha 1 to be 1. Okay, now let's say 2 qubit system. If you have like 2 register, then 2 register, you can simultaneously have 0 0 0 1 1 0 1 1. Okay, with different amplitudes. Again, with the constraint that all of the amplitude, if you take the square and then sum them, they need to add up to 1. And you can scale it up to n qubit system. Basically, the point is that, so if I give you n registers, okay, quantum registers, the point is it can simultaneously represent all possible state, all possible 2 to the n possible states, okay, with the superposition. So we call it a superposition state. The only thing is that each state will have a complex amplitude, okay. So think of it this way: since these numbers could be complex, in particular the numbers could be negative as well, okay. So it is like saying, you know, today it's going to rain with minus 30% chance. Now, in real life, doesn't make sense, right? I mean, what is minus 30% chance? But since in quantum mechanics, these numbers could be negative, it could be complex, it could be negative, it could actually be possible that, you know, a state is in zero, a qubit is actually in zero state with a negative probability. Okay, so that's the fun of it. Like, I mean, and then you might say, like, I mean, why we are doing this, right? I mean, why we are using this kind of math? It actually turns out that the real world actually behaves that way. So we are not making up this math. We are just realizing that the world is actually following this math. Okay, so since the world is following this math, we ask, okay, what happens like if you start to derive equation, you know, from this math? Like, what kind of phenomenon do you get? Okay, so okay, this is the most technical slide of this thing. I promise, like, I won't go into like too much details. Okay, so basically the point here is that, you know, since your state could be in one of the few different possible states simultaneously with different amplitude, you can actually, you know, rotate it in the sense that you can change state, right? Like the way we do normal computation is like we have a system. In the next time frame, we go into a different state. Okay, since it's in a superposition, you can actually rotate and you can actually go into a different state. Okay, but then this has this one thing that, you know, it could be in a superposition, but when you actually measure, you actually see one of the possible state. So you might have seen like news articles where people are saying that, you know, quantum computer can actually simultaneously represent all possible number at once, and you can perform one operation where you are doing all this operation at once, right? Which is true, but the problem is you cannot extract the information. Even though it's in superposition of all those possible numbers, when you try to see it, okay, what state is inside, you will only see one state. So just to going back to this vector example, right? It was either 0 or 1. So the state could be, you know, in a superposition of like 0 with certain probability, 1 with certain probability. But if you try to see it, you will see 0 with alpha 0 square. You will see 1 with alpha 1 square. So you'll only see classical data. Now, as an algorithm designer, your goal is to, you know, don't look at the system and kind of, you know, make this probabilities change in a way such that the probabilities around the right answer concentrates and probabilities around the wrong answers goes down. Okay, so I'll just give you one example of okay, so before I go there, so this slide, you know, so if you start doing maths using this mathematics, okay, you will develop all the, you know, phenomenon of quantum computing that we know. I mean that we usually talk about. You know, you can do no cloning theorem. You know, you can do quantum teleportation, you can do quantum entanglement. All these are manifestation of this math actually. Okay, so you might have heard, you know, that in quantum computing you can teleport, you know, like you can teleport a quantum data from here to Mars or something. So that is true, right? But it is not surprising if you start to do the math. So I'll just give you one example, okay? Like why this computation that we are talking about, it's not that crazy, okay? It's just that the math is slightly different. So let us look at probabilistic computation. So you must have heard of randomized computation, right? Like, you know, like we sometimes do like sometimes, so there is like one famous saying that I heard, like one of the professor in our field, he never spends too much time at the airport. He barely goes an hour ago before the flight leaves. Okay, so then somebody asked, like, why do you do that? So then he said, you know, if you have never missed a flight, then you are spending too much time at the airport. Okay, this means that you are playing deterministic. You don't want to make any mistake. You don't want to never miss your flight. That means you are spending a lot of time. But on the other hand, if you want to have a slight chance of error, in the sense that you have the slight chance of missing the flight, then you can actually optimize on the time. Okay, so the randomized algorithm actually work that way. So you have a little bit of randomness. So you say that, okay, I'm ready to tolerate a little bit of error. So the computation could be wrong sometime, but the positive side is that you actually save on time. So that is actually randomized computation. But one way to look at randomized computation is to look at this way. You take a machine, connect it to a casino dial. So that generates the random number, feed it to the machine, and it does the computation. Okay, so the thing is, you can actually do computation with it. Okay, you can actually do computation with randomization. So let me tell you how. Okay, so let's say if I have a coin. Okay, so I actually have a coin in my pocket. So if you have a coin, the coin could be head or tail, right? Let's say the coin is like not unbiased, but actually biased. So let's say the coin is like, the probability of seeing 1/3 is head, probability of seeing tail is 2/3. Okay, so if I toss it, let's say with probability 2/3, you see tail. Okay, so now what I can do is that I can throw the coin in the air, I can catch it, okay, without actually looking at it, and then now if I look, if I ask you, okay, whether it's head or tail, what is the chance that it's head? What are you going to say? You're going to say it's 0.33% chance that it's going to be head, right? It's 0.66% chance that it is going to be tail, right? But you can actually flip it without looking. Now, what are the chances of seeing your head and tail? It has flipped, right? Now your chances of seeing head is 0.6. Your chances of seeing tail is 0.3. So see, what I'm doing is that I'm taking a random object and I'm performing an operation on it, which is this NOT operation, right? But there's a difference here, which is, you might say, oh, but the state is actually, it's not in a superposition, right? I mean, even if I'm tossing the coin, I'm holding in my hand, it's just my knowledge that I don't know in which state it is, right? So I'm representing it using this vector. But the coin is, of course, like in one of the possible state. So this is true for probabilistic machine. Okay, for quantum, this is, however, not true. For quantum, it's actually in superposition. So we have a couple of experiments like which proves that, you know, a quantum system actually goes into superposition, where it's actually in, like, you know, two different states simultaneously. So it is so I'll skip this slide. So this is actually, you know, the same kind of math with probabilistic machine. The difference is that here we are using norm 1, there we use norm 2. That's the only difference. Okay, and the complex number, in normal probability we use real number. Okay, so now the fun slides. Okay, like you might ask, okay, why then quantum computer if it is like so simple? Like, why do you use it? What's the crux here? The main thing is that, since, remember, like I told you that the probabilities could be negative, right? Here, the thing is that since the probabilities could be negative, some paths can actually cancel out. So for instance, let's say you are doing something like, you know, this is the classical scenario, right? You say that, you know, I toss a coin, and then, you know, depending on the outcome, I'm going to again toss a coin. Okay, and then if the second toss is like 0 or something, I'm going to do something. Okay, so you are essentially here or here. Okay, so what are the probability that you are here or here? In classical probability, you just add them together. So it's like half times half 1/4, and half times half 1/4. So them add together, it's half, right? But in quantum, since the probabilities could be negative, your chances of coming here is -half. Your chances of coming, so this would be one would be plus. Okay, so there's a typo here. So your chance of coming here, let's say half. Your chance of going there is -half. So they can actually cancel each other. So then the probability that you see 0 would be 0. So the point is that here probabilities can actually cancel each other. So that's the main point. Okay, and because of this interference, it could be either destructive or constructive. We are seeing a different pattern in quantum computing. Okay, and as algorithm designer, your goal is to kind of use that, okay, and design new algorithm. Okay, so all the maths are over. If you're you can wake up now if you want. Okay, so okay, so what's the use, right? What's the use of such machine? There could be many different uses. Okay, but in a sense, from computer science perspective, you can actually broadly classify them into this 4 different categories. The first category is, of course, like what Feynman was saying, right? Given a quantum system, we want to simulate it in a quantum computer. So use the first category, which is quantum simulation. Okay. The second category would, of course, be quantum machine learning. Okay, we are using like classical machine learning. Why not do quantum? Now, when we say quantum machine learning, there could be 4 different things. You could do either, the kind of things that we are doing currently with the machine learning, this GPT-4, Chat GPT, and all that is classical machine learning on classical data. Okay, if you have quantum, you can do quantum machine learning on classical data. You could do classical machine learning on quantum data, or you could do quantum machine learning on quantum data. Okay, so there could be 4 different categories, and people are studying all of this. The third and fourth category is the topic that I'm mostly interested in. Okay, which is quantum cryptography and using quantum to solve computational problems. Okay, so what is quantum cryptography? So basically, you have this quantum phenomenon where you want to use it to do cryptography, but so, and then the goal is that we will do something that are not classically possible or intractable. Okay, and the fourth category, which is solving computational problem, is essentially the problem that we have been talking about, which is how do you use quantum computer to speed up some process, like to solve a problem which is classically hard, but using quantum you can do it fast. Okay, so let me quickly tell my team here. Okay, so my team consists of these people right now. So the first two, Thomas and David, they are actually they're my PhD student. Thomas is my PhD student. David used to be my master student, who is actually transiting into PhD in the fall. Both of them are actually look into quantum speed up. Okay, Thomas is mainly looking at the kind of stuff that I'm going to talk mostly. David is actually looking at quantum algorithm, but this is out of scope of this talk, so I'm not going to talk about it. Shreya is actually a master student, and she's she, along with Tyler, Ryan, and Sadashiva. So Sadashiva, Tyler, and Ryan, they are actually undergrad students. They are more into programming side. Okay, so they're doing some project which involves programming. And I also have an upcoming student, Shabnam, in the coming fall, and she's mostly into like quantum cryptography. Okay, so this is my team, but the question is what do we look at? Okay, so first question that is very close to my heart, which is looking at quantum advantage. Okay, like for exactly what kind of problem quantum gives you advantage. Okay, now if you look at quantum, first if we ask this question, like for what kind of problem quantum is faster than normal supercomputers, we need to see what's the landscape classically. Okay, what's the landscape if you take out the quantum? Okay, so then the interesting landscape is actually, you have P, you have NP, you have P space, all that. Okay, what is P? So P is essentially, think of like all the problems, the class of all the problems that we can solve efficiently. Okay, and NP is the problems, the class of all the problems that we can check efficiently. Okay, I'm going to tell you more details about NP. Okay, and BQP is, think of like the class of problems that quantum computer can solve. So we don't exactly know where it sits, so it is this dotted line over there. So maybe it is solving some of the NP problems. The hope is that you don't solve all of the NP problems, okay, but at least some of the problems it can solve. So basically the whole point is to figure out where this dotted line is. Okay, what is this exactly where quantum computation sits? Okay, so okay, I'll stop for a second. Like any questions so far?
Whatever is constructed right now, do you think there's a Moore's law like saying the qubits, like the number of qubits we can work on?
Yeah, that's a good question. So yeah, actually that will be the takeaway message from this talk as well, which is we don't expect to have speed up for all possible function. Okay, so quantum computer is most probably is not going to give you speed up for all the problems. Okay, and actually we know that it's not going to give you speed up for all the problems. And in fact, not for all the practical important problems as well. But the point here is that to understand for exactly what kind of optimization task quantum computer is going to give you speed up. Okay, so then what would happen in the future is that when you are running your big task, okay, when you break it into small chunks, and then you realize that, okay, you know, this part is quantum friendly, you know, this part, for this part quantum can be helpful, so you run that in a quantum machine. For the rest of them, you still run it in a supercomputer. So yes, so it's going to help in terms of Moore's law, but it's not going to, yeah, it's not going to be for all possible functions. So in general, it cannot be expected to continue on the Moore's law's path. Okay, so let me briefly talk about, like, I mean, what is quantum speedup in this context. What do we mean by that? Okay, so when we look at any problem, we actually look at the problem in terms of Boolean functions, meaning you give me a problem to solve, I'll first convert it into decision problem. Okay, I'll first convert it into yes no answer, and then try to solve it. And then you might ask, like, why? Is because, like, it has, we understand that this problem, if you solve it, you can actually, most of the time, you can actually solve this decision problem, use this decision problem to actually find the solution as well. Okay, so just to give you one example, if you ask me, okay, what is the distance from here to Manhattan, right? So that's a question that doesn't have yes no answer, but I can turn it into this question. I can say, like, oh, is the distance from here to Manhattan less than 100 miles? So the answer is be yes, right? And then I'll ask, okay, is the distance from here to Manhattan 50 miles? You will say no, right? So then I can, just by doing this binary search, I can pinpoint, like, what the distance is. So if the decision problem you can solve pretty easily, you can actually, in the same complexity, you can solve the search problem as well. Okay, so we are going to focus on this kind of thing, and moreover, we'll actually look at this problem in query complexity setting, which is, we ask, like, you know, how many locations of the input do you need to read in order to solve the problem? And most of the quantum algorithms are actually manifested in this model, so we actually look at here, and where do we stand, right, in terms of this Boolean function? What do we know so far in terms of quantum speedup? So it turns out that, you know, if you give me function where you care about all possible instances, then quantum computer would not help you, at least in this query model. Okay, would not help you figure out to give you faster algorithm. So what do I mean by all possible inputs? It means you come up with a task. Okay, so imagine, like, your task is something like that. Okay, where you have all possible input and you have all possible outputs, and you want that you don't want to delete any of the input at all. Okay, you want to be fine, you want to be perfectly working program, you want a perfectly working program for all possible input. Then quantum computer cannot give you super polynomial advantage, that we know. But if you want to, you know, like, sacrifice on some of the inputs, meaning, you know, you say that, you know, I'll delete some of the cases, like, I don't care about, you know, some of the cases. And which is true in many applications, right? We don't want, like, all possible inputs. We want, like, only few possible inputs to where the program needs to be correct. Then we know that you can have speed up. So, but again, like, I mean, what are those problems where, you know, like, where, you know, the problem is not defined on all possible inputs? So we call it a partial function. So you have the partial functions, and the question is, if you are given this partial functions, what structure does it need to have in order to have quantum speedup? Okay, and note that when I say quantum speedup, I really want that quantum computer to be outperforming classical computer by a lot of margin, right? Like, exponentially outperforming. Because if it is, like, slightly better, then you won't, like, invest a lot of money into it, right? So we want to pinpoint those problems for which quantum computer gives you speed up, in the sense that the quantum computer maybe solves it, like, in few seconds, and to solve the same problem, the classical computer would take, like, 10,000 years or something of that regime. Okay, so you typically, in complexity term, we call it, like, exponential speed up in terms of the input size. Okay, so maybe the if the input size is n, quantum is like log n, classical is like n, something of that order. Okay, so what we know is that, you know, if your function is symmetric, even though it's partial, okay, even all the possible inputs are not there, again, it cannot have speed up. We also know that if you have other group structure, if you have group structure in your function, then you also don't have any speed up. Okay, but on the other hand, we are starting to see like what possible structure do you need in your problem. So what do you mean by that? So what I mean by is that if you start with a total function, okay, if you start with a function where all the inputs are defined, you kind of chop off some of the inputs, and then we are saying that you could have exponential speed up. But that's not always true, in the sense that if you arbitrarily chop off inputs, then you won't get speed up. Okay, so the question is, for how do you exactly chop it off? So that is kind of the theme that we are after. And it turns out that so far what we understand is that in order to have quantum speed up, you need some global structure in your problem. Okay, so what do I mean by global structure? So it means that, you know, so if I don't give you any structure at all, I tell you that, you know, you need to, so let's say we are in the library, right? We have this database, like huge database of the file, and you store all the file without any structure. Okay, that's kind of mess, right? You don't want to do that. But let's say you take all the book, just, I don't know, arrange randomly, okay, and then you want to find a particular book. What's the hope? There is no structure. Okay, you guys maintain really nice structure so that, you know, you can actually go and find the book pretty quickly. But let's say no structure at all. Can quantum computer find that book faster than classical? It turns out that it can find, but the speed up you get only quadratic. So for instance, if the classical computer, there are like 100 books, the classical computer, let's say, finds it in 100 step, quantum computer can find it in 10 step. Okay, so you get like quadratic in terms of n. Okay, but it's only quadratic. It's not like exponential speed up if there is no structure. On the other hand, if you take a structured problem like this, okay, where the inputs are, you know, really structured that way, then you get like a lot of speed up. So the point here is that just by looking at, you know, like some pathological example, we look at like few examples, and we see that, you know, those problems for which quantum is giving you speed up versus those problems that are not giving you exponential speed up, we see that you need some form of structure. So the question is, what kind of structure? Okay, so that is exactly what we are after. So that is the work that I'm doing with Thomas. We are trying to understand exactly what structure do you need. Okay, how do you sculpt? What is the property of the promise that you need in order to have super polynomial speed up? Okay, so as I told you, like, I'm not going to talk about work with David, because he's mostly into, like, you know, designing quantum algorithms. That is a different work where, you know, you take some task and your goal is to design quantum algorithm. You're not really comparing with classical, but of course your goal would be to outperform classical, of course, right? Okay, so now I'm going to switch gear a little bit. Okay, now if you haven't been following, you can actually start following again. Okay, which is, remember, like I was talking about this NP problem, right? So I was talking about NP, and this is kind of like what my recent grant is about. Okay, so this work is actually related to that. So it is the question of, you know, what is the power of a quantum witness? Now, what does it mean to have a quantum witness? Okay, so let us see what is a witness. So you can actually think of witness in terms of this kind of game, where you have a prover, in a sense, a person who is like all powerful. It can do any computation at any time. Okay, doesn't matter. It can, given any problem, it can just solve any problem, come up with the solution instantly. Okay, but this person is computationally limited, just like a normal human being. Okay, and what we want is that we want this guy to send some witness, in the sense like some data, which would let this person check whether the solution is correct or not. Okay, so let me further elaborate what do I mean by that. So let's look at these two examples. Okay, so first of all, let's look at this Sudoku puzzle. Okay, now what I can do is that how long would it take to solve this Sudoku puzzle? Maybe a lot of time, right? If you try to run a program, you might run into exponentiation, because, you know, you try all possibility, and then sometime there are non-deterministic path that you need to take. Okay, but if I give you a solution to the Sudoku puzzle, how long will it take for you to verify that this is the correct solution? Not much, right? Because you can just, if I give you all the numbers which are missing, you will just check whether you have like 9 numbers everywhere, right? Every row, every column, every box or not. So it's very easy for you to check whether a solution is easy or not, provided the solution. So somebody has to give you the solution, only then you can check easily. Okay, the similar example is that one. Like for instance, let's say I tell you that, from Stony Brook, I tell you that from Stony Brook to Manhattan, you can actually go there. There is a route which can take you to Manhattan, which is like less than 50 miles. Let's say that's my claim. Okay, and maybe how do you find that? Maybe, you drive to Manhattan by exploring all possible different way, and then you check one route every day to figure out whether it's less than 50 miles or not. If there is a route which is less than 50 miles, if somebody gives you the route in the map, you can actually be convinced, right? But if there is no route which is less than 50 miles, no matter what somebody tells you, you will never be convinced. Because if the route is less than 50 miles, if the distance from here to Manhattan is more than 50 miles, nobody can fool me, right? So this prover verifier has this kind of property that, every time there exists a solution, the prover would be able to convince this verifier that it's a right solution. But if the solution is false, then the verifier would never be able to, convince the verifier. So that's the crux of NP. You can actually look at like the complexity class NP that way. My question is about understanding what happens if you replace this witness. So we call it a witness, okay, that the prover is sending. What if it's a quantum? What property do you get? Okay, does it help you in any sense? We know that, of course, this is at least as powerful as classical. So whatever you can do using a normal classical witness, you can do it with quantum. But the question is, can you do, better? So that's exactly, if you go into this quantum regime, your classes, instead of becoming NP, it becomes like QMA. Okay, and then you can ask all sort of different questions like, okay, what's its power? What do you want to do? And my recent proposal is about actually this thing. Like, we want to understand what are its power. Okay, we want to know whether it is unclonable. We want to know whether, it's better than classical. Can it speed up normal computation? If it has been proven that you cannot, the quantum doesn't help. Okay, so it's basically exploring this kind of witness. Okay, so when we say witness, it's not really, the witness of like a crime or something. It's the word witness is used is because it's really like a certificate. Okay, so we call it a certificate or witness. It's like some data that lets you verify some computation, some fact. So that's why we call it witness. Okay. So okay, so I have like yeah. So I have like another 10 minutes, right? So I think I'll go into especially this copyability factor. I have like 2-3 more slides, but I'll take a brief pause, like if you have any question. Yes. So what I do is that I don't use quantum computation. So all my work are actually theory. So what I do is like I prove theorems about quantum computers. I take all the maths and then try to prove whether there is speed up or not, or come up with algorithms. So for instance, I never do any simulation or never use quantum computation, at least for now. Yeah. Right. Yeah. So it is like, you can think of like entanglement is a phenomenon where 2 qubits, which are like really far away, they can be connected in a nicer way, in the sense that, so that's why we use the word entanglement. Okay, so to think of it this way, that you have two qubits which are connected in a way that if you measure this in a particular basis, and you can choose like whatever basis you want. So let's say you choose the 0-1 basis. Okay, like you want to see whether it's 0 or 1, and if you see 0, the other part you will also see 0. If you see 1, the other part you will also see 1. Okay, but that's not the magic here. I mean, of course, like, I mean, they can be 0, 1, you can do it classically as well. The magic is that you can measure in whatever basis you want. The whatever output you get here, the other part you will also get the same output. But you can't really use that to send a signal, right? So there might be this thought that, since, whatever I'm seeing, the other party will also see. And sometimes the representation is this way, that, oh, if I see it, the probability of seeing, the data is like really proportion to like in what basis I'm measuring. But whenever I see it, simultaneously the other party's data also gets converted to, it's like if I see 0, the other party's data also gets converted to 0. But you're not really sending any signals. I mean, whenever the other party measures it without your knowledge, they also see it like a random data, one of these things. The property that that is giving this thing is giving us is that whenever they measure, it would be correlated. So this correlation is the property. Okay.
Quantum computing is very hard, and every time I think I get it, I have to kind of restart again.
Right. Yeah. I mean, this is yeah.
Some companies worried about
well, so there are two things here. First of all, of course, like, I mean, when we have full-fledged quantum computer, you can run source, right? And you can break all the not all, most of the cryptography that we have been using now. So you cannot really stop that, because of course, like if the hacker has copied it, I mean, there's no way you can stop that. But the way people are reacting is like, before we get a quantum computer, when we can no longer use RSA, the hope is to design a protocol that is quantum resilient, like which is harder for a quantum computer to break. Okay, so that's why NIST here has come up with a contest where they're asking people to come up with submissions of the protocol where the protocols are resilient, or at least believed to be harder for quantum computer to break. Okay, so that's like one thing that you want to do. The another aspect is actually using quantum to come up with crypto system that you cannot do classically. Okay, and one of the things is actually quantum key distribution. You have probably heard of this term BB84. It is, and that is one of the fascinating thing that about quantum is that unknown quantum data cannot be cloned. Okay, so if you don't know the data, you cannot clone it perfectly. And this is not true for classical, by the way, right? Like, for instance, if I send you a message, like normal message, nobody can stop you to copy it. And when you copy it, the other player would not even know that you have copied it. But quantumly, if you try to copy an unknown message, you will inevitably destroy it a little bit. So it actually gets detected. So based on this idea, actually there is a crypto system called BB84 crypto system, which was actually discovered in BB84. So it was 84, okay, by two scientists named Gil Brassard and Charlie Bennett. And what they came up with this crypto scheme where if you don't detect any malicious player in between, then there is this guarantee that nobody has tampered with it. Okay, so quantum is actually not only creating problem for current crypto system, is giving you option to solve it. But of course, like practical implementation is another issue, because the security relies on that you send one photon. But what we are realizing is that you try to send these days, and then instead of sending, the apparatus sending one photon is sending 50 photons. So that's totally breaking the scheme. Okay, so you don't want to do that. So practically implementing is another issue. Okay, so we are trying to get there. But this is actually a nice point to talk about this. Like, I mean, I want to talk about unclonability, which is actually, this quantum money that I wanted to talk about. So actually, this even before BB84, Wisner actually came up with the concept of quantum money. And what he said is like, if you use quantum data as a money, then nobody can clone it. So because classical money, it can be counterfeited, right? Like, sure, maybe you don't have the technology at your home, but maybe somebody sophisticated might have the technology, right? So there is nothing stopping them from copying a currency bill. But if you have an unknown quantum data, we know that unknown quantum data cannot be copied perfectly, because it will get detected. So his idea was that why not make a quantum money? Okay, Of course, I mean, you need to, these days, quantum data is very hard to keep, right? You need all those sophisticated machines to keep it like coherent for like so small scale time. But here we are talking about quantum money and keeping it in your pocket, right? So it's like really like a future application. But at least from the theory side, you can make a quantum money that cannot be copied. So that was his original idea. And now we are wondering, you know, what else can you do in the unclonability setting, right? You use this property of quantum unclonability, and then the point would be, what can you do? And one of the applications could be quantum software, which I'm interested in actually, which is, you know, if I give you, I don't know, a movie or something in a CD, you can essentially copy it. But if you use a quantum CD, we know that, you know, if you don't know the actual data, you won't be able to perfectly copy it without getting detected. So then the question is, can you do softwares using quantum? And that's the whole area of, you know, unclonable softwares. I'm interested in that. And but here in particular for this project, I'm interested in knowing, you know, can you, given such witness, can you make it unclonable? And it turns out that we can. So we can actually make for the whole NP, we can actually make it unclonable. Like in the sense, like you can design a proof system which, given any NP witness, you can actually make it unclonable. Okay, so I'll stop here. Okay, and I would like to stop with this slide over here, which says that, you know, like we have quantum computer that we have been using, like we are trying to design, right? But look at this picture. This is a picture of ENIAC. Okay, so here it shows that if few scientists or technicians, they were actually working on this machine, and the machines used to be gigantic, right? And it used to take like a whole room, like a huge room, to store one computer. But at the end, what did these machines do? Like maybe multiply two numbers. But then once we had transistor, the whole thing changes. Okay, now we have machine in our pocket, right? And which is drastically, you know, like a powerful than this kind of machine. And if you look at quantum computer, we are actually at this stage right now. Right now, the quantum computers are actually, you know, kept in like, you know, like a really giant room, and then the quantum computer is actually very tiny. You have like 400 qubits, and, you know, really bragging about it, right? So we are kind of at the same stage. So once we discover quantum transistor, or we just one technology away, when we do this, our quantum computer will also be smaller. But we don't expect it to, you know, be in our pocket. But at least, I mean, we expect it to be at least a larger scalable system. Okay, so with that, I'll stop. Prediction about? Oh, like where it will be useful, you mean? Right. Yeah, my prediction is that it won't be applicable in the sense like it won't transform the whole, you know, like landscape of computation. Like it's not going to replace classical machine like supercomputers. We'd still be using supercomputers. The point here is that we will eventually figure out for exactly what kind of problems quantum will give you speed up. Okay, right now we are seeing patterns, but we exactly don't understand. We are seeing few problems. Okay, so once we understand that, in future what would happen is that we'll just classify all those problems for which quantum gives you speed up, and furthermore we'll also know why it gives you speed up. Okay, or why it doesn't give you speed up. And once you know that, future compiler will have that in the system. Like every time you try to run a big program and the compiler breaks up into small chunks, then, you know, like you just figure out like which component is like quantum friendly, you run it in a quantum server. So I see the future as a hybrid machine, you know, not like a fully quantum machine, not like a fully classical machine, but it would be a hybrid machine. So yeah, I think that's my prediction.
When?
Oh, when? Okay. Okay, so the point here is that we actually have quantum computer even today, right? We have, like, IBM has already made this machine which is like 450 qubits. Now the question is, can you really use it? So, you know, like for many years, like we theoretician, we have been saying that, you know, let the physicists are not making quantum computers, right? Let them make it. Meanwhile, what we can do is that we can just try to understand it, from the maths perspective, and then we can try to design algorithm for the full-fledged machine. When you design full-fledged machine, we are going to run it. Okay. Now the physicists are catching up. They are actually building this quantum machine, which is like 400, 500 qubits. And now they're looking at us and they're saying, okay, give us problems that we can run in these machines. For what problems even these machines can give you advantage? And the problem is we don't know that. Okay, so right now there is a whole field called NISQ era computation, okay, which is noisy intermediate scale quantum computation, which is, we know that, okay, we can build these machines which are like like small scale machine. Can you take advantage of it somehow? So in terms of predictions, like, I mean, we already have that, and right now we are trying to understand what this small scale machine is capable of. In fact, we are even not there. So the first thing we are trying to show is that these machines are actually better than classical. So there is this whole proof of quantumness concept where let's say you are a company, right? And then you are building a quantum computer, and then you are claiming it to be quantum computer. How would I trust that it is actually a quantum computer and not a supercomputer that you are running, right? For instance, like the IBM machine, like the typical access that you get to the machine without paying is like 15 or 16 qubit machine, right? But 16 qubits you can do it with a supercomputer. So how do you know that they're actually running a quantum machine? So right now we are trying to come up with different tests as a community, which if you run, the quantum machine would be able to run efficiently, but then it will come with the mathematical guarantee that a classical machine would not be able to perform within like 10,000 years or something. So that's the first hope. Once we get that, we will prove that these systems are better than classical machine. And then the next step would be to figure out exactly what kind of practical problems we can solve. So yes, a lot of unknowns, but yeah, exciting times. I mean, it's like the early age of classical computation. It's exactly like this picture. Like, I mean, at that time, we knew how computation work. We actually knew it before that. Actually, we knew automata before all this thing. So we exactly knew the math that if the technology catch up, and if you could use your electronics to which can change state, if you could do that, then you can make a machine. We knew that from very early stage. With quantum, we have the same thing. We know the math, but we don't know exactly for what problems you can solve it. We know the actual functionality, but imagine even at that time, like there were like not many classical algorithms that were known, right? Like the classical algorithms have been discovered over the ages, and right now we have like you look at like algorithm book, there are like so many algorithms, but they have been discovered over like the span of 100 years. So we are at that stage. Like we give it some time, like another, I don't know, 20, 30 years, we'll have a huge, like a collection of quantum algorithms. And then we'll also have the machine. And by that time, our understanding would also be better about like what these machines are capable of and not capable of. And then we'll find the usefulness. But right now, yeah, it is kind of difficult to tell, like, I mean, what the use would be right now.
So would it be compared to like the EV and also the gas vehicle? So quantum might be at some point in the future, and then it might be independent, but still coexist with the classical.
That's right. That's right. Yeah. I mean, so EV, for instance, is going to totally disrupt, in my opinion, like all the gas-based like automobile, right? But with quantum computing, it's not going to be the case. With quantum computing, it's not going to replace the classical computer. Like we are not going to use like everybody. We're not like all of us are not going to use quantum computer on day-to-day basis, because it is too expensive. It's also too cumbersome in the sense that you can do all the classical computation using a quantum machine, but the threshold is very high. Like you don't want to do all those things in a quantum machine. Like we have really powerful supercomputers to do normal tasks. But like if you try to do anything interesting, we actually run into interactable problems. Actually, many of the things are actually interactable. Like for instance, you try to schedule, and some of the very normal looking problem becomes intractable. Like, just to give you one example, let's say we have this university, right? We want to schedule lecture in different lecture halls, and we want to be as optimum as possible, right? We want to, like the class size is small, we want to schedule it in this lecture hall versus the other one, right? And we want to make sure that when one class ends, the other class doesn't start with the overlapping time, but in some other time. So if you want to do it optimally, it turns out that it becomes NP complete. So you cannot hope to find a solution which is going to give you optimal. So what we do is, like these days, is approximate solution. Okay, so the hope is that quantum computer would not help you in solving this problem because it's NP complete, but at least some other optimization problem. So, and we actually call it NP intermediate problems. Okay, NP intermediate, the source factoring algorithm actually sits there. Another problem is graph isomorphism. Okay, so the hope is that at least for some of the problems in NP intermediate family, quantum computer would give us its advantage. Yeah.
Thank you.
Yeah.
Any other questions? So then we. Oh.
Yeah.
Speaking of environmental protection, can humans be replaced by cats?
Yeah, that's a very good question. Yeah, qubits can be replaced by cats as long as you don't look inside the box. You also need to give it a little bit of poison, which you are not allowed to do. Like all the organization, I mean, would come after you. Yeah. Yeah.
You mentioned that certain problems of life and for anybody be structured, but what if it's there's almost
Right. Right. Yeah, that's a very good question. So that's exactly if I go back to this slide over here, so we know that, yeah, if the books are like, totally randomly sorted, then it gives you quadratic speedup. But you might have little bit of structure, and at some point you will see quantum effect. And the question is, like, when you are happy, right? I mean, even for totally unstructured search, you are still getting quadratic speedup. So what it turns out that if you put little bit of structure, there could be some problem which is slightly faster than classical algorithm. Okay, and so far the problem that we are seeing with exponential speedup is actually has a lot of structure. But now recently there are results where we are actually taking out the structure from the problems. Okay, so there are like recent, like from last year, where the problem doesn't have any structure, yet you have a search problem which you can formulate in a way that you have you can still get like exponential speedup. Okay, so to answer your question, exactly like what type of structure do you need to put in your problem to get like certain advantage? It's not very clear right now. Okay, all we know is that, if you don't have any structure, then you have this. We know that, under certain structure, quantum can give you speed up, but there is no general procedure which, when you come up with a problem, and then, like I just look at the structure and tell you how much quantum speed up you are going to get. So unfortunately, there's no procedure as such right now. But the goal of complexity theory is to exactly do that, like come up with a procedure which will look at a function and tell you whether it's going to give you speed up or not. Sure.
random library.
Right. Right. That's right. So basically the context would be slightly different. Like if you don't know what structure is there, the algorithm that you run is still like unstructured algorithm, right? But the thing is that if you tell me that there is structure, then I will design a quantum algorithm to harness that problem, right? But for instance, if you learn, like let's say you run the Grover's algorithm, which is designed for unstructured search, right? You might give it structured data. That's completely legit thing to do, right? it will still do this, the algorithm that it was supposed to do. So it's not taking advantage of the structure that might be there. So if you don't know the structure, then yes, the chances that the problem would not, the algorithm would not find this actual structure and take advantage of it. Okay, but the point is, if you put some structure and let the algorithm designer know a priori, then he's gonna design an algorithm which will take advantage of that fact. Yeah. Yes.
Wondering who's financing the research? Is it sort of quote pure science? Or are there particular bodies within the governments which are interested in this?
So right now, for instance, my research is, this research is getting funded by Department of Energy. But my position, for instance, is funded by National Science Foundation. But there are like many other agencies that also funds. Like for instance, what we do is like we look for fundings everywhere. There are some private players as well. But more generally, most of the funding is from NSF. But these days, many other agencies are also taking interest in quantum. And Department of Energy is one of them. Usually Department of Defense, there are like many things are under that, like Air Force and Navy and many other organizations. They are also interested in quantum, but for them it's more like application based. Like you need to find a problem which kind of benefits them in a way.
They will help find the problem.
Well, like you propose a problem that has they need to like it. And they will like it only when it kind of benefits them in a certain way, right? But NSF is like more general. So for any theoretical research, NSF is the way to go. But you can also get funding from, like, I don't know, Google, Amazon, because they are interested in quantum. They're building quantum, so they're interested in knowing, you know, like how, like in general, like investment into quantum community. So a lot of private players as well. Yeah. Actually, there are many things, right? You take any classical type of area, you can start doing quantum and start asking, you know, can I do quantum in it? So for instance, just to give you one example, people are doing, you know, like maybe finance, right? Like Wall Street, they're doing finance and they're very interested in like optimizing, you know, like, can you, I don't know, optimize money, right? If you come up with an idea to use quantum computer to have advantages in quantum finance, then even the Wall Street Bank would be interested. And there's actually, believe it or not, there are areas called quantum finance and people are looking into it. Machine learning is another thing which has like a lot of funding, where the goal is that exactly to take advantage of quantum, can you somehow speed up all the process that we have in machine learning? So yeah, in general, like, yeah, I mean there are monies in various aspects, but it kind of like your research has to match their need. Only then they fund you.
Yes, very much interested, but they're not earning enough money. They don't get it yet. So you do the 65% industry. I think there's like 3 or 4 billion. Compared to China, that's big. So if in terms of like this potential balance around kind of pushing the boundaries, but it's still slow.
Yeah, but the situation is improving actually. Like if you look at like I don't know, 4 or 5 years ago, there's like no funding in quantum at all. And then people realized that, you know, this is something that we really need to focus on. And I remember that at some point when I was pursuing my PhD, only few players were doing really good in quantum. Like, you know, like in Canada, IQC had like, so Canadian government was putting a lot of money. At that point, like there's not much investment here. And all the people there doing quantum are like big institutes like MIT or like Caltech or something. But there's like no general money in that sense. But that actually changed like around like 2018 or 2019 when the government agencies realized that, you know, this is something important and we need to do to catch up with other players. And then, you know, a lot of funding started pouring in.
Is quantum research. What the other countries do?
No, I think it's doing better right now compared to many other countries. Yeah, I think even like Canada, it's doing better. Yeah, in terms of, yeah.
Any other questions? Okay, thank you all for coming.
Mhm.
Thank you so
Yeah,
much.
thank
for
you.
your interesting
Yeah,
talk.
thank you so much.
Oh, very interesting.
Thanks so much.
Uh,
Contact you.